Okay, so what is a neural base of attention? The key features to consider visual attention is the distinction between top-down and bottom-up, spatial, temporal, feature, object-based attention, which type of attention we are talking about, and then the hierarchical organization of the visual cortex. Okay, and there are many types of the attention that is not visual as well, auditory and also arousal, but most of the what we know about attention is coming from the visual science. So these are quite important kind of consideration. And then another key features to consider is competing neuronal interactions operating or underlying the attention. And neuronal interaction wise, I talked a little bit about the neuronal model of the visual binocular library last week. And this is also highly relevant for attention. So first, just to go back to a couple of weeks ago of knowledge, I emphasized that there is this architectural kind of feature of the visual system where the receptive field size expands as you go from lower visual area to higher area. So for example, if the center of the receptive field is here, the B1 receptive field is small, and then B2 tends to be bigger. But again, this is a bit confounded by the fact that the eccentricity also goes up. So when you are fixating here, and then if the same eccentricity size is kept, probably B1 neurons tend to be like this size at this location, and B2, and then B4, and then IT, kind of. That's a sort of the structure of the receptive field. So this particular figure from Christoph Koch's work is a bit exaggerated because it confounds both eccentricity and the size effect of the receptive field. But nonetheless, generally speaking, at the given location, receptive field becomes bigger as you go across the hierarchy. Okay, and then the key concept here is that what you are, if you are imagining that you are the neurons in, let's say, IT, okay, and then if you are receiving the input from the B4, then the B4 neurons might say that, oh, there is a phase here, or phase here, or not phase here, and not phase here. And the IT has to make a sort of the computation, and then eventually it seems to be doing the phase detection as a function. And that could be regardless of where the phase is within this IT's receptive field. And to achieve that kind of function, what it needs to do is to consider or sort of weight the evidence from lower visual areas to trust or make a decision of what kind of information to pass on to downstream neurons. Okay, and I'm going to give a very simplistic neuronal model of how it can be achieved. It can achieve such a computation in the next slides. So first, let's consider retinal stimulus. Presentation of the stimulus looks like this rectangle, and then let's suppose that subjects are fixating at this location. So it's projected on the left visual field, and then this is a rectangle. And then, as you might have already learned, all these left hemifield stimulus is going to be presented or processed on the right hemifield of the B2. Okay, and then there is some kind of cortical magnification and so on, but I'll leave it for now. And then suppose you find a neurons that responds to all these four edges corresponding to this one. It's flipped, but I'll just to simplify, I'm not going to talk about the flipping of the side and also up and down. And then you also find neurons in V4, and that appears to be connected from V2 in a way that this neuron that detects this line at this location to be projecting into this V4 neurons and so on. And then as a whole, this V4 neuron detects a shape like this, rectangle or square in this particular location. And you can find something like this in V4 IT, but this is a sort of model neuron, okay? And then for our purpose, what's important is what happens in terms of neuronal response. And then over the time here, let's suppose that I don't present this stimulus, square stimulus initially, and then at time 0, I present it for, let's say, up until 1 second, okay? And then after that, it's off. And then just simplifying all these response, I simplify that, all these neurons immediately respond and then do not decay and so on. Then I show the firing rate of each of the neurons here. So this goes from 0 to, let's say, 50 hertz, and then this also goes to 0 to 50 and so on for each of the neurons. And then this model V4 neuron would be also excited by each of these inputs, and then it fires like crazy, but it saturates its firing rate at some point. So let's say it goes from 0 to 50 hertz or something like that. Okay, that's how this neuron would respond when there is no attentional situation and just presenting as stimulus that V4 likes. Now, consider the next situation where I present only the stimulus in one of the edge for this square, and then nothing, or very weak stimulus for the rest. And then this particular neuron that prefers this location and this orientation still continues to fire from 50 hertz. Okay, but the input into this V4 neurons are much weaker to other 3 location. And this guy is the only one that produces very strong 50 hertz inputs. And as a result, it produces slightly less firing rate, okay, compared to when it produces very striking a strong input with 4 squares and so on. And remember that I said that these squares are much just weaker and not really absent. So it's still, we can see it as a sort of square in this case. All right, then the next situation. So suppose that I present one of the location as a non-compatible or non-preferred stimulus for this particular neuron. And it could be colored in red, but this is just for the visualization purpose. So instead of this nice triangle, now I present this unclear kind of stimulus. And in particular, this stimulus is going to suppress the V2 neurons here, okay? So here, the neurons are going to respond, usually at 50 hertz, but it becomes much weaker in terms of firing rate. So it goes like, this baseline, almost like baseline firing rate. It's kind of difficult to draw, but you know what I mean. So it gets, lower firing rate for this particular neuron. And then that generates, and the other neurons are, also weakly exciting this, B4 neurons and so on. And this neuron actually, now that, it's much weaker than the, usual firing rate, it actually provides the inhibitory inputs to this neuron. And as a result, although, some of these nicely kind of looking faint square-like stimulus generates a little bit of the firing, it generates overall much weaker firing rate. So non-preferred stimulus inhibits V2 neuron, and V2 neurons inhibit further the V4 neurons when it's incompatible with the overall shape of the preference. Okay. So that up to here, it's nothing to do with attention. It's just a purely the sort of simultaneous recording type experiment between B2 and B4 with a different stimulus preference. And then the important consideration comes when those preferred stimulus in the top right and non-preferred stimulus in the bottom left is simultaneously presented. So in this situation, B2 neuron top right is going to fire a lot, and then the top left and bottom left is going to be inhibited or suppressing other neurons. And what happens in terms of B4 neurons? Assuming that monkeys are doing, or humans for that matter, are doing something neutral to these two stimulus, what's happening is usually something like this. So B2 neurons are firing like a preferred or non-preferred stimulus, as I explained before. And then B4 neurons tend to fire intermediate between the suppressed situation by non-preferred stimulus alone or preferred stimulus alone. And it's intermediate. So it's not super complex, okay? And then what attention does is to bias this firing of the B4 neuron in one way or the other. So for example, if some kind of attentional mechanism kicks in and then select and amplify a little bit of this guy, and then if there is an interactive sort of interaction between this neuron to this neuron, then there can be some kind of inhibitory inputs here. And then that also, cuts all these, inhibitory activity from B2 to B4 is now suppressed. And as a result, what you tend to see is that the B2 doesn't change much, in terms of observed firing rate, because, but at the B4, you see, recovery of the attentional effect of the response due to attentional effects in this case. So that's this kind of, response. Recovery through the attentional amplification. And, within B2, it can be the case that, this attention can change a little bit of the firing, but it doesn't have to be very strong as long as this B2 to B4 activation coming from many neurons in line with this idea. And that tends to be what we observe in the neurophysiology experiment. On the other hand, if you attend or some kind of attentional biasing signal amplifies this neuron's firing, and then this neuron is interacting with this neuron and then suppress the firing, what happens? So now B2 neurons, which this may be a bit confusing, but that neurons that prefer this orientation becomes active and enhanced by the attention, and that guy can suppress this neuron. And then as a result, the strong inhibition is still there, and then the excitation from this nice neuron is not there anymore. So now, as a result, overall, B4 neuron response tends to become closer to when stimulus was presented here alone. I hope this is clear. Okay. And then Reynolds, John Reynolds has done exactly this kind of experiment in monkey B4. And what they found is summarized in this figure. So as I said, the baseline condition here, that is both stimulus presented is intermediate compared to the good stimulus, preferred stimulus alone, or poor stimulus alone here, right? For the particular neuron. On the other hand, this when the preferred stimulus is attended, then this both stimulus situation, the stimulus itself is the same here and then here, but now response of the neurons are almost the same as when the good stimulus was presented alone. Okay. On the other hand, when the poor stimulus was attended by the monkey by some task instruction or task relevance, then although the stimulus itself is the same, but the response of the B4 neurons almost looks like first stimulus alone. So this kind of idea is compatible with the fact that, when you attend to some stimulus, then that's, consistent. That's what we become aware of. Okay, so this is the type of neurons in B4 that goes with attention and perception. And I mentioned in the beginning that there is a class of attention now, which is called feature-based attention. And in the case of the feature-based attention, the task tends to be something like manipulated by the instruction. For example, here the task instruction is indicated by the color of the fixation cross, either white or black. And then your task is to report the orientation of the color that matches with this, central fixation. So here, after stimulus presentation, you need to remember all the, stimulus and then attend to all of them. But then at the discrimination phase, you need to report, oh, it was, so this is a, left hand. In this case of the trial, you need to report the orientation of the white stimulus. So you are going to press the button for left tilted or something like that. On the other hand, this black one trial, you need to report in the end black orientation. So it's right in this case. And so the key here is that the instruction is different between the match and non-match condition. On the other hand, during this stimulus presentation period, that's the most critical recording period for this experiment. Everything except for this central fixation point is the same. And then the researcher can record the neurons that have a receptive field around here, right? And then you can make the stimulus either preferred or non-preferred for this particular V4 neuron. Okay, and then when you do the recording in this situation, what they found was something like this. So when the monkeys, the neurons preferred stimulus was presented, here this is a preferred stimulus, okay? And then the task instruction is matching with the feature of this, preferred stimulus. Then the firing rate is very high and then sustained. However, when the unpreferred stimulus is attended here, okay? So it's a non-matching situation. Your preference of the neuron does not match with what the monkey is trying to do, which is to remember black, pattern. So monkey is presumably attending to all these black thing. Then this white orientation, which actually neuron prefers, gets suppressed. And this is sort of the similar kind of mechanism, through the similar kind of mechanism that I explained before about spatial attention that John Reynolds reported. Okay, it's a bit different kind of mechanism, but idea is similar. Okay, so just to summarize the neural basis of attention so far, the core principles of the bias competition model of attention is that first, attentional effect gets stronger when the stimulus itself induces a lot of competition. Okay, unless there is a stimulus, then you can't operate this inhibitory mechanism between the neurons. And for the neuron to operate on attention or benefit from attention, neuron has to receive many inputs from many different kind of neurons, and that kind of situation is expected to occur with the higher visual areas, which has the neurons that has a larger receptive field, like IT or FFA or PPA or V4 compared to V1, V2. These guys are likely to be benefiting from attention because there is a potential competitive candidates. And psychologically, all of this can translate that when some biasing process operates. So this part I haven't actually explained, but instruction, expectation, or memory template matching kind of stuff happens then this biasing signal can operate and result in attentional modification. And if all of the things work together, then as a result, conscious perception can drastically change without change in the stimulus, which is what we wanted to achieve. Okay. So what is the source of the biasing signal, which I haven't actually discussed yet? And one of the most likely candidates is this frontal or parietal area. And when they are impaired, some of the patients exhibit neglect or extinction. And that's what we're going to see with the video.
Because Alan's middle often isn't it?
The middle is the right.
And it's always eat on the right side, but not on the left side. Just leave that.
Give her a dinner plate, and she'd only eat the vegetables and leave the meat, which is disappointing because I was a cook.
So if you start to picture, it can not fit in the paper if he gets over to the left, because he hasn't left enough room.
Spatial neglect is a syndrome, that is signs and symptoms that patients most frequently have after stroke, but sometimes in forms of Alzheimer's disease, where they ignore one side of space. So people, objects and sounds on one side tend to get ignored, and the patients who have it tend to be drawn to the other side. And this can extend to things like the food on the plate in front of them, that only eat food on this side and then say they're finished. It may extend to parts of their own body, so when trying to shave, they may only shave this side of the face and miss out this side, put makeup on.
So you can only see from across there?
Yeah, from there to there. That's my vision.
So what's going on in the other half?
Nothing.
There's nothing at all.
Because often I've come up from this side to give you something.
Anybody can creep up my left, I wouldn't know they were there.
See anything.
I can't sense them.
So if you just look at me and just point at the finger that moves, okay? Or say both of both. Tell me which finger moves.
First one.
Okay.
That one.
Okay.
No.
Look at me.
That one.
Okay. Look at me.
That one. That one. That one. That one. That one.
Great. That's good. They tend not to describe the condition, to be honest. One of the most intriguing things about it is that this sort of loss of attention for one side of space doesn't leave a great gaping hole. And that's why it's very useful to contrast it when someone's got what's called a hemianopia, which is a primary sensory deficit. They can't see that side of things, and they know they can't see it. So they're constantly moving their heads like that. Whereas patients with neglect are unaware of their deficit, that they're not even aware that they're missing something, because their sort of imagination of space has gone on that side too.
Does he have a name?
I don't know, I haven't thought of one.
I can stand right next to you, can't I? You can't sense one there.
No, you can't. If you told her to look, she'd actually look around that way, like that, right round on the right-hand side, and then come back to central. She wouldn't actually think about coming and looking around to the left as well.
People often say, why don't you just tell them to look to the left? And relatives can be very frustrated about this too. And I think you've got to be aware that the process of attention and these higher visual areas are involved in the representation of space, rather than just seeing things where they are. See the lines there?
Split in the middle.
Yeah, that's one end, that's the other end. Show me where the middle is. Mark the middle for me.
I was only looking at a line from there to there.
Mm.
It's in the middle of my line, not the middle of your line.
So the first time I saw you, that's where you were marking the centre of the line as well. Patients realise something's wrong when things are pointed out to them over and over and over again. So in a way, I think for them it's slightly abstract, that they know that there's some problem on the left-hand side, and they're not aware of that problem, but they know everybody's telling them they have to do something more on the left. And so they use strategies, things like that, to try and overcome the problem without really being able to appreciate it in its fullness.
I remember getting those word search books, and I remember it was only one side was always ever filled in. Yeah, and then slowly she got better and better at it, because I used to say to her, Colby, you know, I'm not getting value for money here, you're only doing half the time. Yeah, so slowly she learned that, yeah, start learn, you know, do the left side first and then come back to the right.
Some people have it soon after their stroke, and it gets better within a few weeks. And then another group of people have it long term and learn strategies to overcome it. So if you probe deeply, they still have problems with attention. Even that bias may go away, but they still have deep problems when trying to find things. And then they also tend not to remember where things are after they've looked at them. They have poor working memory for space as well. So a lot of these deficits don't recover, although people can use strategies to overcome them.
Give that a please if they find you. That's good.
Okay, so the video basically showed the patients who have a likely lesion in the frontal or parietal areas, and as a result, it tends to generate neglect or extinction, as explained by the patient's report. And these tend to happen from the right side of the parietal cortex. That's a sort of classic story about the neglect or extinction. And neuronally, what's more clearly found these days over the last 20 years is that the involvement of the frontal areas in monkeys. So here, FEF is the area called frontal eye field. It is very important to control for the eye movements, and without this, you know, monkey cannot make an eye movements. Frontal eye field. And this side is eyes, and then this is a B1. Okay, so it's located in quite far, you know, front. And then what they this Moore's Turing-Moore's experiment did was first to locate the receptive field of the B4 neurons. Okay, as I said, you know, B4 is. So what this Turing-Moore's paper did first is locate and characterize the neurons in B4's preferred stimulus, and also the receptive field location and extent. So here, monkey is fixating at here at the center, and the bottom left is the location of the B4, which is located to the right side of the B4 in the top, you know, dorsal areas. Okay, and then when the stimulus was presented like here, this is over time. And then when the stimulus comes on, B4 neurons start to fire really like crazy when it's preferred stimulus. Okay. And then on the other hand, FEF, frontal eye field, they put electrodes for the micro stimulation. And FEF is known to generate eye movements, especially when it's produced, you know, when the stimulation magnitude is strong. So like, you know, patients stimulated in FFA, if you do it with a human, then, and also if the extent is really micro, then most likely columnar organization of the FEF allows the neurons within the FFA, which has a similar preferred, you know, movement field, or the target of the motion of the eye movement, to get activated together, and then that induces eye movement. So here, one particular area of the FEF stimulation resulted in the movement of the eyes toward the bottom left here. So eye position goes from nothing to something here. And then this is the duration of the FEF stimulation. Okay, so the setup is that B4 is recorded, and then FEF is also stimulated, and then they match the location of the B4 receptive field and FEF movement field or eye movement field. This is very demanding kind of experiment, and that's why in 2003 it went to Nature, the top journal. And then what they found is the following. So if the receptive field and the movement field matches, then when the stimulus is presented from here, time 0, and then 500 milliseconds, then V4 neuron starts to fire a lot and then decline like this. And then around this time, black is the one without stimulation. But around 500 milliseconds, if they start to stimulate FEF a little bit so that it doesn't induce eye movements, then that's the reason why they present this horizontal and also vertical eye movement trace. So this stimulation doesn't cause eye movement at all here, right? And then what happened was that the V4 neurons firing rate systematically enhanced. The red is the part that is a recording average of V4 neurons. So what it means is that when there is a subthreshold activity in FEF that doesn't induce eye movements, it still increases the firing rate of the V4. And that corresponds to our sort of the covert shift of attention. Covert shift of attention, according to this type of the experiment, can be explained by sort of a subthreshold eye movement, which shifts attention only, and then response at the attended location becomes enhanced, almost like when you are preparing the movement to that area. That's the sort of the finding here. And the important thing for us is that this kind of biasing type of idea that I introduce in the simple model can be coming from a frontal area, in this case FEF. So with this much of what I told you about attention, neural basis of attention, source of attention in the frontal palatal area, and also a competition from B to B4 interaction, can we actually explain attention-related blindness? To some extent, we should be able to. For example, in attentional or change blindness situation, as you remember from the demonstration, typically these stimulus contain lots of complicated stimulus. Like in the case of the initial change blindness, you saw that there is a natural scene, and the natural scene itself contains lots of people and objects like cars, grass, and things like that. And then in the case of the change blindness, you don't know what to attend. So many of the things are sort of competing each other, and then especially periphery, it becomes kind of suppressed or enhanced depending on the chance. And to notice the difference, you need to sustain change and also after change, before and after change kind of stimulus. And usually your attention actually shifts much faster compared to this change. So over the time, you don't remember the change, even momentarily. And that's one way to explain change blindness. And in attention blindness of the gorilla thing, remember that that video first asks you to pay attention to the white t-shirt team. And that means that the feature-based attention to the white becomes very strong. And on the other hand, to make this feature-based attentional enhancement for the white, you also simultaneously have to suppress the black team's t-shirt, right? Because it is competing, in fact. And because this black thing is in general really suppressed, and that's probably the reason why gorilla is not experienced really strongly, because it is actually suppressing, actively. And attention blink and masking is also similarly explained in terms of the temporal version of this competition idea, probably. And the important thing is that all of this is potentially explained by the failure of the signal amplification and also too much of the suppression. And that leads to this idea of global workspace theory of consciousness. So here is a very complicated 2x2 design matrix or sort of the table. And let me go through first the row. The row is the strength of the bottom-up stimulus. And you can think of this as a sort of stimulus contrast or duration and so on during the masking. And it can be either weak or strong. And then top-down attention component here can be either absent or present. And then when it's absent, this model suggests that things that is coming from frontal or parietal doesn't reach the visual cortex. So the weak or interrupted things just doesn't get activation or amplification, and then no reportability result. And basically it's a subliminal, non-conscious, unattended. And then if the stimulus is sufficiently strong, then what they call is a pre-conscious stage. So it is an intense activation of the occipital area like V1 to V4, potentially FFA and also IT, but it's confined to sensory motor processes. And then occipital or temporal cortex generates some kind of loopy activity and the local synchrony. And then it still doesn't result in reportability because attention is now occupied somewhere here. This is a somewhere symbol. And they don't call it as conscious. On the other hand, then when the stimulus is weak but still amplified by attention, this model says that attention can reach to enhance a bit of this occipital. And then it enhances the feed-forward activation up to, let's say FFA and so on. But it doesn't lead to a very sufficient kind of strength of the activation because stimulus is weak from the beginning. And as a result, it doesn't lead into the front parietal activity. And we can't also see it, and then we can't report it as a consciously seen stimulus. What distinguishes, according to this global workspace theory, is this conscious state requiring both top-down attention amplification and sufficiently strong stimulus. And that is, in a sense, marriage of the prefrontal and parietal amplification signal and the bottom-up signal strength itself. And this corresponds to intense activation of the parietal frontal network and long-distance synchrony and the conscious reportability. Okay, this is the global workspace theory. And at this point, I should say that I'm not very convinced by this model, but that's going to be coming to the from the next week. Okay, but this is a highly popular model in the consciousness research right now. So, in summary, in this section, I explained the neural basis of attention. And it's primarily coming from the biasing signal from the frontal or parietal cortex, and that tries to resolve the competition. And for this to work, you need an overlapping receptive field in a very large kind. So that's likely to be located in higher visual areas and bigger overlap between the receptive field. And then one of the most promising model to explain this attention and consciousness relationship is this global neuronal workspace theory, GNW. And this can explain various aspects of attention-related reports of blindness through the failure of amplification of the top-down, by the top-down attention and reaching to the global workspace. So global workspace basically explains something is reportable when it reaches, when something is strong enough and amplified enough so that it reaches to frontal and parietal area. And this tries to primarily explain the conscious reports. But at the time of the proposal, people didn't really distinguish between conscious experience per se versus conscious reports, or at least we didn't have a tool to dissociate these two. And so that became quite, popular. And as I argue in the next weeks, now we can have a couple of, interesting situations that can tell the difference between experience perceived versus conscious reports. And one of the biggest kind of problem of the global neural workspace is that the link between the neural activity and the consciousness remains really unclear. So it is explained that something that enters into the frontal apparatus areas becomes conscious. But what I reviewed until last week is that these sensory areas such as V4, or IT, or FFA, all these local areas of the network generates conscious experience of the color or motion or face and objects. And input to the parietal or frontal area may be slightly different for each of the different kind of qualia, but how this differential input pattern, if there is anything, can distinguish what we experience is unclear. So they need to probably propose or think about the way that prefrontal apparatus areas kind of decodes or transforms the input pattern into conscious experience, but that part is never explained, because primarily global neural workspace is a theory about how it's possible that we can report something, but not in other situations. So the next week, we are going to address several of the questions. So this is a bit of the preview. Is attention necessary when there is no competition? So I talked about many of the neural bases of the attention as a sort of the coming from the competition. So if there is no competition to begin with, is there any role for the top-down attention? That's one question. And then can this biased competition model explain the findings of the dual task? That's another question. I briefly mentioned, and if you see the demo and then try to do it by yourself, it has been shown that natural seeing, animal presence or absence, or vehicle presence or absence, or face gender, these kind of things are possible to do under the dual task. However, the disk orientation discrimination, red-green versus green-red, that's not possible under the dual task situation. In both cases, it seems like there are lots of competition going on, but only the case of the green-red seems to be a case where we can't see we need an attentional amplification. So there seems to be something more than the biased competition that attention is doing. And what's that is still unclear. Potentially it's a binding, but it's a sort of a frontier of consciousness. And then lastly, if you think about the biased competition model or global workspace theory, then attention should be able to operate on both visible and invisible stimulus. And this is a kind of the dissociation that drove the last 20 years of the attention consciousness research. And we are going to talk about it next week. See you later.